How's everyone doing today? Shimon, Garima, Chase, Maya, and Justin coming at you with information on remote sensing. In this video, we'll be discussing the definition of remote sensing, common types of sensors, as well as the orbits used for data collection. We'll also talk about how remote sensing is used to model Earth's weather patterns, the stability and precision of sensors in terms of attitude, as well as past and present missions that utilize this type of technique. So, what is it? Remote sensing is a technique to obtain information on the surface of planetary bodies at a particular distance with the use of satellites and aircraft. Common applications include weather monitoring, polar observation, and mapping the Earth's topography using electromagnetic waves. For most of the applications, the energy from the sun, which is reflected off the Earth's surface, is observed by the satellites with sensors on board of varying resolutions of different applications. The wide variety of different sensor types and orbital orientations that satellites use for remote sensing allow for study of various planetary phenomena.
There are two types of remote sensors for data collection: passive sensors and active sensors. Passive sensors work by using energy from the sun and detecting the radiation from a target source. This data can then be analyzed to measure the attributes of the target, like surface temperature and cloud formations. One drawback to this type of sensing is that it cannot penetrate dense clouds, making it difficult to get constant measurements of properties that lie below where the cloud cover forms. Some examples of passive sensors are radiometers, accelerometers, spectroradiometers, all of which are used to measure the land and sea surface temperatures, vegetation properties, cloud and aerosol properties, and other physical properties. Active sensors provide their own energy source and work by emitting radiation at a target and measuring the reflected radiation. Active sensors tend to operate only in the microwave portion of the electromagnetic spectrum, while passive sensors are able to operate in a wider range. Active sensors can be used even with dense cloud cover, making them good for measuring things like precipitation and winds. Some examples of active sensors are laser altimeters, ranging instruments, and radar. Both types of sensors are used in monitoring Earth's weather and topography.
For remote sensing, various types of orbits are used for collecting different types of data. For example, the polar or sun synchronous orbit is used to observe the entire globe, including the poles. The Suomi National Polar Orbiting Partnership by NASA/NOAA uses this type of orbit for remote sensing. And the non-polar low Earth orbit is used to provide information on a specific range of latitudes, as this orbit is quite close to the surface of the Earth. And this orbit is used by the Global Precipitation Mission by NASA. And lastly, a geostationary orbit is another orbit that is used for remote sensing. And this orbit is used to provide coverage of one specific area as the orbit travels at the same rate as the Earth's rotation, meaning it rests on one location on the Earth. The geostationary operational environmental satellite, which is operated by United States NOAA, uses this specific orbit, and its pictures below are shown respectively from left to right. To use remote sensing for the Earth weather model, weather satellites use microwave wavelengths, a form of electromagnetic waves. Because these types of wavelengths can pass through the clouds, satellites with geostationary orbits provide continuous coverage using precise temporal resolution, which is the time it takes for a satellite to complete an orbit and come back to the original area. Precise temporal resolution also depends on the satellite sensors as well as the orbit. Specifically, the Japanese Advanced Microwave Scanning Radiometer on board NASA's Aqua satellite, shown in the picture below, uses microwave wavelengths to get high-resolution microwave measurements of the whole polar region, even if the clouds may seem to obstruct the vision of the spacecraft.
Due to the various reasons for launching remote sensing satellite missions, such as military endeavors, GPS and mapping companies, Earth topography imaging, and analysis, among others, the importance for stability and precision on these spacecraft is paramount. It would not be worth the exorbitant amount of finances to pay for a satellite that returns imprecise, incomplete, or subpar data for these missions. The reason why stability and precision is a necessary topic is due to the disturbances that cause the spacecraft to rotate, usually in an undesirable direction. These rotations will decrease the accuracy of sensors, antennas, cameras, and most other data acquisition devices on board the spacecraft. The main disturbance torques the spacecraft will experience are due to aerodynamic drag, electromagnetic induction, solar radiation pressure, gravity gradients, and micrometeorite disturbances. This image shows the equations to calculate the torque applied to the spacecraft from 4 of the 5 aforementioned major disturbance torques. As you can see, the magnitude and direction of the torques imparted on the spacecraft due to these disturbances depend on many aspects, including the spacecraft characteristics, location, speed, and the characteristics of the disturbance fields or forces themselves. However, some of the torques may actually be used to benefit the attitude of the spacecraft. For example, implementing a space tether on the vehicle to harness gravity gradient torques for stabilization and sensor pointing precision in the nadir, anti-Earth, or any other directions desired to be fixed in the LVLH frame. Different missions have different thresholds for how stable and precise the spacecraft must be during orbit in order to deem the mission operational. These values are listed as accuracy analysis, and here are some examples. For high-resolution imaging missions, the pointing accuracy must be no greater than 0.5 microradians, and the angular velocity errors cannot exceed 10 microradians per second. Space environment and weather observation missions must not exceed a plus or minus 1 degree in consistency, and communication satellite antenna must be pointed within a half degree of the intended target.
Since humans first launched satellites into space, there have been various missions that have used remote sensing to gather information about the Earth, both in the past and present. These satellites are often used to gather data about the atmosphere, ocean, and landscape of the Earth. Some examples of current remote sensing missions are the Global Precipitation Mission, which uses an active radar to map and track rain and snowfall over time from orbit to give us a better understanding of Earth's water and energy cycles, weather forecasting, and properties of precipitation. The Sea-WIFS project, which uses multiple active spectrometers to gather quantitative data on global ocean biooptical properties. The Aura-OMI mission that uses an active, wide field of view spectrometer to distinguish between aerosol types such as smoke, dust, and sulfates, and measures cloud pressure and coverage. And finally, the geostationary operational environmental satellite that uses active spectrometers and radar to predict severe weather. The first significant orbital remote sensing missions began in 1959 with the Vanguard 2 weather satellite developed by the U.S. Navy, and 1960 with the Corona program satellites developed by the United States government for use in photographing the Soviet Union during the Cold War. These are some images and diagrams of the satellites listed on the previous slide from top to bottom, respectively left to right.
To summarize, remote sensing satellites use 3 kinds of orbits for data collection: polar, non-polar LEO, and geostationary. Weather monitoring satellites, such as the Geostationary Operational Environmental Satellite, use geostationary orbits for data collection and utilizes both passive and active sensors. Passive sensors are unable to observe areas with dense cloud cover since they use the energy of the sun, whereas active sensors are able to penetrate the atmosphere at most conditions. Additionally, stability analysis is especially important for remote sensing satellites to ensure the satellites are pointing in the appropriate direction for proper data collection, especially when disturbance torques on the spacecraft affects its attitude and orientation.